Welcome everyone to the Third Coast Water Seminar Series. My name is Elena Harkness. I'm the Executive Director of Current Innovation, and we are the organizing partner of the Third Coast Water Seminar Series. I'm really happy to be welcoming you all to this final Third Coast seminar of 2020. As you may know, we initiated this series this year in partnership with a tremendous group of research partners listed here: Northwestern University, Argonne National Laboratory, the University of Illinois at Chicago, University of Chicago, and the University of Illinois Urbana-Champaign. And we all came together with the notion that a collaborative endeavor to advance the innovation horizon for water research would be valuable to our community. And we're really excited to be bringing you the third installment of that series today, which will continue into 2021. Just a quick reminder on logistics. This is a Zoom webinar, and so we'd love you to submit your questions in the Q&A tab, and I'll be moderating questions for our presenter today. If you have general comments or want to talk to your peers who are on the call, please go ahead and do that in the chat tab. That's open to you this time. And finally, this event is being recorded. We find a valuable part of our community building is to be able to share these out. So you'll be able to get the link to this program after it concludes on Current's event page and YouTube channel. We'll also send it out to all registered attendees post-event. A brief agenda for today. As always, our Third Coast Water Seminar Series is focused on spotlighting a significant researcher in the water community. And today I'm very excited to be introducing Dr. Meagan Mauter, who's the Associate Professor of Civil and Environmental Engineering and Center Fellow at the Woods Institute for the Environment, Director, Water and Energy Efficiency for the Environment Lab, all of that at Stanford University. So we'll be hearing from Meagan today, speaking on using desalination to close the circular economy in water. Very excited about this topic. Then we'll have audience Q&A and we'll wrap it up. But again, Meagan's the focus and we're really excited to have her here to share with us today. A little bit of background, why we're all here. We're here because everyone in this community, everybody that's part of the Third Coast Water Seminar Series or part of Current's community, cares about our water future. We all share the conviction that we need more healthy water to drink, less floodwater in our basements. And we know that no matter what the water challenge is, innovative approaches to solutions are often much too large or much too complicated for any one actor to solve alone. The collaboration that problem solving in water requires takes partnerships, and Current exists to build those bridges, to strengthen those networks between the individuals, the entrepreneurs, the utilities, the government partners, nonprofits, investors, and of course, highlighted here today, the research community, everyone willing to take rational risks, to push the boundaries of what's possible and try new solutions. Current does this by being an unbiased advocate for the best solutions and policies wherever we can find them, whatever sector, wherever they're coming from in the world. We try to stay on top of the latest in water tech. We know this field is changing so rapidly, but our job is to scan this horizon and understand what's out there. We then independently assess that technology and we try to understand where it's best deployed, what problems it's best matched to solve, and then we recommend solutions, either for others to try or sometimes on occasion for us to pilot ourselves. So that's how we work, and one of the great examples of the collaborative endeavors that Current has helped to build is right here today in the Third Coast Water Seminar Series. So I'm going to turn it over now to one of our key partners, Junhong Chen from Argonne National Laboratory and the University of Chicago, to introduce our speaker. Junhong?
Thank you, Elena. Good afternoon, everyone. I would like to add my own welcome to all of you to the Third Coast Water Seminar Series. My name is Junhong Chen. I'm a professor in the Prisco School of Molecular Engineering at the University of Chicago. I also have a joint appointment at Argonne National Laboratory as the lab's lead water strategist. So it is my great pleasure to introduce our speaker today, Dr. Meagan Mauter. Dr. Mauter received her double bachelor's degree in civil and environmental engineering and history from Rice University. So very interesting combination. And also a master's of environmental engineering from Rice University as well, and a PhD in chemical and environmental engineering from Yale University. She then completed her postdoctoral training at the Harvard Kennedy School of Government, where she was an Energy Technology Innovation Policy Fellow. Dr. Mauter is currently an Associate Professor of Civil and Environmental Engineering at Stanford University. She's also a Center Fellow by courtesy in the Woods Institute for the Environment. Perhaps most importantly, Dr. Mauter serves as the research director for the National Alliance for Water Innovation, NAWI, the only hub, DOE hub on water. This is a $110 million DOE energy water desalination hub to address water security issues in the US. The hub targets early stage research and development and energy efficient and cost competitive technologies for desalinating non-traditional source waters. I'm sure Meagan is going to talk about it. Dr. Mauter also serves as several editorial advisory boards, such as EST Letters and ACS Sustainable Chemistry and Engineering. She has received many awards, including the NSF Career Award. Without further ado, please join me in welcoming Dr. Meagan Mauter. Off to you, Meagan.
Thank you, Jung-Ho. I'm going to go ahead and share my screen here. Okay, can everyone see that? Great. So I want to just thank everyone for the kind introduction and generally say that it's an honor to be here, not only representing the work that my group has done, researching the technology needs and analysis needs to provide desalination technologies that will enhance the circular water economy. But I am also here representing NAWI, the National Alliance for Water Innovation. And I think, Elena, your introduction about the kind of scope that current occupies is really nicely complemented by the mission of NAWI, which is to fund lower stage research, so more basic research in water desalination technologies that will enable a circular water economy. So I want to start out by thanking my group. I have a really amazing team of students and postdocs that have performed a lot of this work, as well as the entire NAWI Alliance community. We are a completely open organization, so anyone who would like to join can apply to become an Alliance member free of cost. We just kicked off our first annual meeting last week when we had over 500 attendees there. So this is really a large and growing alliance that is kind of nucleated around a set of 25-ish consortium members where a great deal of the first year R&D activities are happening. So the work that I present today is certainly an amalgamation of work that I've done in my own group, but also has been deeply inspired by my research community within the National Alliance for Water Innovation. So I'm going to start out really by sharing with you some of NAWI's core tenets and why we are so focused on water desalination research to enable a circular water economy. And then I want to transition into a deeper dive discussion about the tools that we need to really inform our R&D investments. The current consortium is all about innovation. And so I thought it would be a nice opportunity to share some of my most recent work on tools for innovation and how we really decide where to invest R&D dollars as a research community. So first, I'll just say that today's water supply is really built on this 20th century linear model of accessing fresh water sources, large centralized treatment facilities that leverage economies of scale, and the ability to discharge wastewater with pretty limited regulations and oversight. One of the issues is that this does not hold as a model for the 21st century. We are having really large changes in precipitation patterns. We have increased water demand, especially in urban environments. Our urban water infrastructure is aging and needs upgrading and replacement. And there are increasingly stringent regulatory limits on discharge. All of these factors are forcing water users to look toward non-traditional water sources and non-traditional treatment methods to address these challenges. And because these water users are looking for low-cost sources, they tend to prefer sources that have lower energy intensities of water treatment. That is to say, lower salinity waters. So we tend to see investment, when we're looking to augment municipal freshwater sources, we tend to see investments in municipal water reuse and brackish water desalination. But what's really interesting about these sources is that municipal wastewater reuse and brackish water desalination are actually far less thermodynamically efficient than our processes for treating seawater. And so we can replot these same sources with respect to their relative energy intensity of treatment, which is the energy intensity of treatment relative to its thermodynamic limit of treatment. And so what you see is that seawater desalination is actually one of the most efficient industrial separation processes, whereas there's a large opportunity for innovation and improvements in other non-traditional source water desalinations at lower salinity ranges and higher salinity ranges. So NAUI's mission is really to help water users cost effectively tap these non-traditional sources, both by pursuing new sources like inland brackish water, as well as by facilitating water reuse. Ultimately, we seek to develop technologies that enable 90% of non-traditional water sources to achieve pipe parity. Translating this mission into an R&D portfolio, though, really begins and ends with how we define and how we measure pipe parity. And I want to dig into pipe parity for the water space a little bit more deeply here. When we talk about pipe parity, the academic research community almost entirely focuses on the energy intensity of treatment. That's what I just presented to you. But the industrial research community and quite frankly, water users are often far more focused on cost. And so metrics for assessing cost become really, really important, especially for emerging technologies. In a lot of our baselining activities that we did in preparation for the hub and then in our first year of activity for the hub, we also heard about the role of other pipe parity metrics and other drivers for water reuse. Things like the role of regulatory discharge or softer value propositions like drought resilience that a seawater desalination facility would provide to a city, or sustainability certifications that an industrial manufacturer might realize by implementing water recycling on site. And so what we found is that there are often a large number of different determining factors, each of which affect a user's willingness to pay a premium for non-traditional water reuse. But let me sort of make this even more concrete by trying to offer up a definition for pipe parity. And of course, I'm going to start by saying pipe parity is defined by the end user. Our working definition acknowledges this reality by saying a non-traditional source water achieves pipe parity when the marginal cost and energy intensity or other metrics are less than or equal to the next available source for a specific end user. We've looked at a lot of different end users in NAUI's baselining and road mapping activities during year one, including the power sector, the resource extraction sector, the industrial sector, the municipal sector, and the agricultural sector. We will also be highlighting in our road mapping and baselining activities the degree to which this is really geographically defined. So we see a lot of variation, and I think it's fun to be here in the Third Coast seminar series because so much of the desalination focus has actually been inland in the West, in places like California and in Arizona and New Mexico, these really arid, more desert regions, but it's equally applicable in other geographic areas where we might not think about being short on water supply, but we see a lot of other drivers that are encouraging water reuse. I will say as well that across these water users, there are actually a common set of technical barriers to cost effectively tapping those non-traditional water supplies. And I'll come back to what those technical barriers are in just a second. The other important sort of definitional aspect to pipe parity is that it must be defined on the margin, which means that it is defined instantaneously and in a location-specific manner. So a non-traditional source water like wastewater is never going to have the same cost or the same energy intensity as fresh surface water. We know that. But for a municipality like Orange County that needs to augment limited supply, wastewater reuse may very well be the next lowest cost source. So on the margin, it is cost competitive. So determining what this next lowest cost source is also means that we need to look beyond just treatment to consider the full life cycle cost of water. And we've done a lot of work in our group to really look at the energy embedded in water transmission, so conveying water from the source to the treatment facility, understanding the energy intensity of treatment with high resolution, and then also quantifying the energy intensity of distributing water from the treatment facility to the consumer. In one example, we've looked at a network of 330 different consumer nodes and quantified the relative energy intensity of this entire process, moving from the source to the consumer for each of these water users. And we observed three things in doing this. The first is that there's a wide range of energy intensity for delivering water to different consumers. I've visualized that on the map here, but we can also look at this in the red line on this plot, where we see that the daily average marginal energy intensity varies by almost a factor of 2. The second takeaway is that the energy intensity is very frequently above the approximate kilowatt hour per cubic meter that we estimate reverse osmosis UV AOP systems for municipal reuse to take. So this suggests that there may be really cost competitive opportunities for water reuse, especially in a distributed setting. And the third takeaway here is that the transmission and distribution energy intensity are often much greater than the energy intensity of treatment for overall municipal systems. And they happen to be on the same order of magnitude as these desalination processes, like I just mentioned. And so this really underscores the fact that there are large opportunities to think differently about the way we might augment future water supplies. In NAUI, we really relied on this quantification work to inform hypotheses about the relationships between treatment costs, transport costs, and total costs when defining the levelized cost of water. And our initial hypothesis was really that the most viable pathway for reducing the cost of non-traditional water sources would be to replace the economies of scale that we tend to see in water treatment, where we see much lower cost water treatment at higher operational scales, with economies of scale in manufacturing, essentially lowering the cost of small scale distributed treatment systems by through manufacturing innovations, and that this would reduce the overall cost of water by basically minimizing or eliminating the cost of water transport. So this is kind of our grand vision for NAUI, and one of the next steps in that was really to define what the technical needs were to realize this, these small scale distributed systems. We identified 6 different technical needs that we thought were going to be critical. The first is autonomous operation, so an ability to operate these small scale systems without as many on-site operators, and also to leverage advanced models to help us work in a more efficient, both thermodynamically efficient and cost-efficient manner. The second innovation need is in precision separations. So we want to be able to remove contaminants of concern without over-treating the water. Most of the time, this involves trying to move away from bulk separation processes when a trace contaminant is what's driving that particular separations need. The third area is a need for resilient treatment systems. And in particular, in small scale systems, we expect to see much greater fluctuation in water quality. And so we're going to need systems that can really respond to this fluctuation without failing, without fouling, without scaling, et cetera. The fourth area is intensified brine management. I'm going to spend a lot of time on this in today's seminar, but essentially brine or the concentrate management from desalination systems is often a real limiting factor in our ability to deploy inland water desal, and so is going to be very important as we move forward with this paradigm. The fifth area is modular, so really leveraging these economies of scale in manufacturing to reduce the costs of both pretreatment and desalination systems. And then finally, process electrification, moving away from chemically intensive processes that are difficult to stock and store on site to electrically driven processes, and then also using water treatment systems themselves to provide services back to the electricity grid. So across these 6 challenge areas, we're able to distill this this kind of set of core research needs that would benefit all of the 5 water user groups that I previously mentioned. But I'll also say that as a funding organization, we're also facing a larger and slightly more existential question about how to distill some of these challenge area questions down to very specific innovation needs that are going to most quickly deliver lower cost desalination systems. And I'll say this is really a universal challenge. It's a challenge for academic researchers that are looking for new R&D projects. It's a challenge for industrial component manufacturers who are looking to stay competitive in their marketplaces. And it's a challenge for municipalities trying to figure out when it's worth adopting a new technology platform or when it's worth waiting a little bit longer to see what comes out next. And the reality is that as a community, as a water community especially, we really lack good tools for evaluating the value of innovation. And so today's talk is going to focus on a suite of approaches that we've been developing in my group and alongside my group within NAUI to really look at this universal question. And I'm going to do this by using intensified brine management as a model. So we start with a high level problem, which is that we don't end up recovering much product water from brines because existing technologies for high salinity brine dewatering are expensive and energy intensive. And so as a result, we incur very, very high disposal costs. The next step is really to figure out what are the technologies that are used today and why are they so expensive, right? So we can start with this baselining question of trying to understand what is the cost and energy intensity of reverse osmosis, which is the state-of-the-art technology for concentrating brines up to about 75 grams per liter, and mechanical vapor recompression, which is the most energy efficient thermal approach for desalination of high salinity brines at this higher salinity from about 75 up to about 250 grams per liter TDS. And so what we find right off the bat is that while reverse osmosis is incredibly energy efficient, mechanical vapor recompression, because it involves the first order phase transition, uses 5 to 10 times more energy and is 3 to 10 times more expensive than seawater reverse osmosis. The next question is really, okay, what are the alternatives? So we're interested in evaluating both the cost and energy benefits of emerging technologies. In this case, I'm going to highlight 3 modular membrane technologies because that falls within the NAUI paradigm of really trying to move ourselves toward modularity and membrane-based systems. But this is by no means a comprehensive list of different approaches. The first one that I want to highlight is high pressure reverse osmosis. So in high pressure RO, you are simply extending the pressure range of existing reverse osmosis systems. So today's RO systems are limited by the pressure tolerance or the burst pressure of our membrane modules, which is typically somewhere between 65 and 85 bar. The issue is that the driving force for water flux is the difference between this change in applied pressure across the membrane and the salinity across the membrane. So as we increase from, say, a seawater feed salinity up to a 70 gram per liter feed water salinity, our driving force, so the size of these red arrows, decreases substantially. So we have a lot of driving force or a lot of flux in the beginning and relatively low flux at the end. So when we're trying to desalinate even higher salinity feeds, we really don't get any flux. In fact, we'd get osmotic transport or flux in the opposite direction to that's desired. So one approach in high pressure reverse osmosis is simply to raise the burst pressure of the membranes. And if we were to do that up to 90 or 125 or even 300 bar, you could really enhance the recovery of existing reverse osmosis systems. And in fact, I think your last Third Coast seminar series speaker, Menachem Elimelech, who is also my PhD advisor, did a lot of work in quantifying the value, the energy benefits of high pressure reverse osmosis. So, doing this would certainly allow us to recover lots and lots of additional water from our saline brines. Another approach is to address this kind of separation at higher salinities by reducing the osmotic pressure difference across the membrane. So in osmotically assisted reverse osmosis, we introduce a saline sweep, which allows us to drive water flux for high salinities at operating pressures that are typical of today's membrane modules. The issue is that this diluted sweep is not actually a useful product. So we need to perform several separation steps. Basically, you introduce a second stage and then a third stage until you can introduce a water that can be effectively treated using standard reverse osmosis. So we were really excited about proposing the osmotically assisted reverse osmosis process back in 2017. There's also some parallel efforts by Gradient doing really nice work in commercializing this technology. But we evaluated the energy savings of deploying osmotically assisted RO, and we're really excited about the potential benefits relative to MVC, which is plotted in the arrows, and osmotically assisted reverse osmosis, which is plotted in these by these black dots. And that's great, but one of the things that we realized as we were exploring the system is that our energy optimal configuration had really, really high costs. So in fact, optimizing the energy intensity of any membrane system is somewhat trivial. You just maximize the membrane area because you're reducing the osmotic pressure difference across the membrane. You can operate more efficiently. But we can't afford to build those systems. And so the cost optimal system is actually the system that has much higher energy intensities for separation. And an underlying issue behind all of this is that it's actually pretty hard to figure out what is that cost optimal design. In osmotically assisted reverse osmosis, we have 6 decision variables per stage that we are adjusting. And so evaluating this parametrically is really close to impossible. The final technology that we've done a lot of work on as a group is membrane distillation. And if you thought osmotically assisted RO was complicated, well, welcome to MD. Membrane distillation is, at its core, a technology that uses a difference in vapor pressure to drive vapor transport across the membrane. You have evaporation on that feed water interface, or the hot side, and then condensation on the cold side, and it's this difference in vapor pressure that drives flux. But when we think about actually building out MD systems, we often see many different gap types. We see lots of different process configurations and then tremendously different superstructures. All of this to say that it is absolutely a non-trivial challenge to estimate the current costs of an OARO or an MD system. Because this design space is so large. And I'd say it's even more difficult to figure out what innovations are going to substantially lower these costs. So we finally took a step back from new process development to really focus on what are the tools that we need to help us make sense of this research and development space. And I'd say that one way that we've found to overcome the first challenge is to use process-based optimization models to rigorously explore the design space. So instead of looking at each combination of decision variables manually, we simply specify the salinity of the incoming feed water and the desired water recovery. And then we also specify the performance of each of the components and the associated costs of those system components, including things like membrane permeability, the cost of energy, the cost of financing, et cetera. So we have a pretty simple set of inputs to these cost optimization models. And then the process-based optimization model itself searches for the system configurations that minimize the levelized cost of water or the CapEx and OpEx amortized over the lifespan of the plant to produce a specific system design. So it specifies the flow rates, I should say, it specifies all of the devices and components, the flow rates, the pressures, et cetera. And it gives you the system design, the operating metrics, and then finally the system costs. So we've been able to apply this to osmotically assisted reverse osmosis as shown here. Again, we have this feed concentration on the x-axis and the water recovery on the y-axis, while the levelized cost of water is plotted as a color gradient. And so what you can see is there are very different, I actually haven't shown you sort of the inner workings of this model, but there are very, very different system designs for each of these cases. But I've given you the cost optimal system design and the associated price. We can now compare this in an apples to apples way with other emerging technologies for high salinity brine treatment, things like looping membrane distillation and multi-stage membrane distillation. And this allows us to start to assess which emerging technology is going to perform best in which salinity range. So you can see that osmotically assisted reverse osmosis with this lighter color yellow is going to perform much better than the other two technologies in this kind of 75 gram per liter range, 50% recovery. It is much, much better. But it also helps us understand whether there are technologies that are just never going to make sense or are unlikely to ever be cost competitive. And in this case, you see very quickly that looping MD is always more expensive than multi-stage MD. And that's really a function of the way that heat is recovered in looping MD relative to multi-stage MD. So this is really helpful in saying, hey, I don't want to spend any more of my postdoc's effort in building looping MD systems. Let's quickly move on and just focus on multi-stage designs. The other thing that we can do with optimization models is conduct sensitivity analysis on the effects of improving component performance. So we can look at this relationship between component performance and this levelized cost of water for the entire system. And this is especially important because membrane systems are really complex assemblies of many different components. And these components all interact with one another. So we can't simply assume a static relationship between the components and the systems. So instead, what we do is we parametrically vary component performance, and then we let the optimization model search for that re-optimized system design. And we can say, okay, as we improve component X, our levelized cost of water is going to come down by this much. So we've done this again for osmotically assisted reverse osmosis. Here I'm showing the effects of doubling the pure water permeability coefficient of a membrane. And what we see is that if we double that A parameter, we can decrease the costs of osmotically assisted reverse osmosis by 5 to 10%, depending on what your feed water salinity is. In contrast, we can ask, what happens if we have the structural parameter of our membrane? If we take it from 1200 to 600. And here we see a 15 to 25% cost reduction. So this helps us understand that R&D activities that focus on reducing structural parameters are going to be more impactful than those that are focused on increasing water permeability. But the issue with this approach is that it naively assumes that increasing component or improving component performance does not increase component costs. And so a more sophisticated variant of this analysis would perform coupled sensitivity analysis on component performance and costs at the same time. So for an increase in performance, we'd specify an associated increase in component costs based on what's available in terms of different component availabilities or a cost curve for a component. And then again, let the optimization model select the cost optimal design and operating parameters. This would produce a three-dimensional map that related cost and performance of the component to the levelized cost of the membrane system. So this is, again, the levelized cost of water for the entire system based on component cost and performance. An interesting feature of this analysis is that it identifies the relationship between component cost and component performance that yields an identical system, LCOW. So you'll see in this white line here, I'm plotting a single line that traces an identical levelized cost of water across a range of component performance and costs. And we call this the isocost curve. So in other words, improving component performance here at the same rate that you improved component costs or increased component costs would basically yield no change in the levelized cost of water. So the goal, of course, is to move beyond this cost curve by either improving component performance or reducing component costs, and doing so in a way that moves us to overall lower levelized costs of water. Okay, so the arrow on that plot should have gone in the other direction. I'm so sorry, minor detail. So these isocost curves could be really helpful in informing high impact innovation trajectories for lowering the overall system costs of water. And when we have curves that are a little bit more vertical, this suggests that only component cost reductions are going to reduce the levelized cost of water for the system. In contrast, if our isocost curves are horizontal, it suggests that only performance improvements are going to reduce the costs of water. And finally, if we have more complex functions, we're really looking for the direction that's normal to that isocost curve to yield the highest impact on the levelized cost of water. So let me relate this back to our example of structural parameters in our membrane systems. You'll see here that we previously suggested that by having the structural parameter of the membrane, we could significantly reduce these system costs. And that's true if you have no change in component costs. But the issue is that if you expect the membrane to cost you more, then you may actually see a component cost change. And so what this map tells us is that you should only focus on having the structural parameter if the associated increase in membrane costs is less than 40%. So anything less than 40%, good to go, you're making an impact. Anything more than 40%, you're actually losing ground. The other thing that this can help us realize is that focusing on having the cost of the membrane would be far more impactful than trying to have the cost of the structural parameter. So it really helps us get at where we might want to invest our R&D dollars. And in fact, we're going to be using some of these cost curves to help us figure out where to invest R&D dollars within our NAUI research portfolio. Because these are unique to each process and device, it certainly requires good models of these systems, and I'll get to that again a little bit at the end of my talk. But this is a quick overview of the isocost curves for osmotically assisted RO and multi-stage MD processes that we've worked to develop so far. I guess I'd just point out too that you consistently see a lot of nonlinearity in these curves, and you also see quite a bit of variation in the magnitude of cost reduction for each. So the larger arrows in these plots indicate the potential for larger reductions in the levelized cost of water. So I've talked a lot about how we can improve component performance or reduce component costs to move us to an improved ISO cost curve. But I haven't really talked about the potential value of diversification of components. So a question that we've also started to look at is what happens if you can't really overcome that ISO cost curve? Is there still value in diversifying the set of components along that curve? And I believe that the answer is yes, mostly because it provides a lever for us to influence the relative ratio of capital expenses to operational expenses in the system. So this ISO cost curve can also be mapped onto this percent of system OPEX, or that ratio of OPEX to total levelized cost of water. And what you see, I have an example here of pump efficiency change in osmotically assisted reverse osmosis, is that we can actually see pretty significant sort of tuning of that ratio of CapEx to OPEX costs for even a single component in a system. And that's valuable because oftentimes, we aren't designing systems that have well-defined lifespans, or we know that, there's a probability or a chance that our system's going to be decommissioned early. And so, we might prefer to have higher operational expenses relative to capital expenses. The final thing that is really important in understanding how to perform analyses on membrane systems is that there's a lot of uncertainty in the future costs of components, especially for emerging technologies, or in this relationship between cost and performance. We just don't know most of the time, right? And there's also, so when we're trying to understand the value of innovation for component A versus component A performance, we need to acknowledge that there's in fact a lot of uncertainty or a lot of distribution here. The second thing that's really important to understand is that there's oftentimes simultaneous component innovation. So our component A will be improving, and at the same time, other components in the system may be improving, either because you've invested in that other component improvement, or because there's spillover effects from other fields where advanced manufacturing techniques in heat exchanger systems in power plants get translated into advanced manufacturing approaches to heat exchanger systems in water treatment systems. And so what we expect is that the value of innovation for the first component is actually going to be affected by the level of performance in the second component. And the reality is that there's not just two components, there's many, many, many components. And so we really need to treat these sources of uncertainty, both in being able to predict values as well as in understanding the effect of coupled systems more explicitly. So we've done a lot of work in the past couple of months developing something that we call the stochastic value of innovation analysis. And I'm going into a little bit of the nitty-gritty here, but I basically want to say that at a high level, what we do is evaluate the effects of improving the performance or reducing the costs of a component parametrically, but in a Monte Carlo based environment. So we establish a range of performance cost parameters and use the Monte Carlo method to sample a reference case. We then improve that reference case by a set amount to value innovation. And this X is defined in a couple of different ways in our system. We can look at a case in which there's no cost penalty. So that's the same as doing sort of a statistically based parametric analysis. In another case, we increase the performance, but we also increase the cost. In a third case, we increase the performance by 1% and we decrease the performance by 1%. So this one's going to be really good. And then in a fourth case, we actually translate this ISO cost curve up. It's a kind of a proxy for what an actual component cost curve might be, even though we don't have actual component cost curves to test here. In theory, if we translate this ISO cost curve based on where this Monte Carlo step has taken us, we should actually see a distribution that's centered around 0 if this translation is fully valid. If it's not fully valid, then we know that our ISO cost curve isn't consistent in those other ranges. And you'll see that there's a variation there when we actually apply these different techniques to osmotically assisted reverse osmosis. So the idea here is that we're looking for distributions that have high impact, or when you increase the performance by 1%, you also improve the levelized cost of water by 1%. But you also are looking for cases in which there's a narrow distribution, because that suggests that there's high certainty that this improvement will actually make a difference, even in the face of innovation and improvements in other components. So I'm not going to walk into any of this with a lot of detail, but I do want to say that we can apply a lot of these methods that we've looked at and that the R&D community might use to also understanding how industrial users might apply these tools to assess the robustness of process technologies to future innovations. So I can look at this set of technologies that I've just talked you through today, reverse osmosis, osmotically assisted RO and MD, and sort of map them in an overall cost curve. I can also ask, what's the effect of improvements in performance and cost reduction across all of the components? And to what extent does that actually lower the costs or change the technology platforms that I'd use? In this case, it substantially lowers costs, which we'd expect, right? But it doesn't really change our technology platforms. So those are pretty robust here. I will say too that I've sort of put high pressure reverse osmosis aside, but we've also incorporated that into our analysis and found that HPRO fully displaces osmotically assisted RO if we can manufacture a membrane with seawater level A and B parameters and costs at 300 bar. The issue is that from a materials science perspective, this is going to be really difficult in practice. So we have everything from membrane compression that changes transport properties to new permeate collection approaches that are likely to change module costs. And so it can be quite difficult to really get at what level of cost changes are going to keep high pressure reverse osmosis cost competitive relative to ideal OARO or MD technologies. And what we found here in an effort to probe the effects of cost changes only, so what we do is basically look at the cost multiplier of the high pressure components and do a willingness to pay analysis. And what we find is that if you maintain performance, you are using high pressure reverse osmosis is beneficial so long as your cost multiplier stays at sort of a lower end of this range, whereas it becomes less advantageous relative to MD and OARO if that cost multiplier increases. So I don't want to go into too much more detail here, but I do want to say that a big goal of NAUI is to make these tools open source for the water research community. And I'm happy to answer any questions that you have about the set of model libraries and simulation and optimization tools that we're developing within the NAUI research community to really help the water treatment community benefit from this type of analysis. In conclusion, I just want to say that I believe that analysis-driven research is going to be critical to identifying these high-impact innovation opportunities. Membrane processes are really complex assemblies of coupled components, and so we need high process-level fidelity. We also need system models that are readily fit into optimization algorithms and can help really be deployed to understand the relative value and utility of emerging technologies and focus our R&D efforts in productive directions. And I'll just say to conclude that all of this cost analysis is really going to benefit from closer collaboration between researchers and industrial manufacturers that have a lot of insight into the actual cost performance curves for many of these systems. So with that, I want to end and take questions, and Lamia, I'll turn it back over to you.
Thanks so much, Megan. That was terrific and such a perfect presentation for this audience, where we do always hope to bring sort of the research and industry together to talk about how to collaboratively address these issues. So we have a great queue of questions, and I'm going to try to synthesize some since we're a little short on time. So the first, I think, just concerns the potential disincentive for really, really novel technologies when you're thinking about how to model out the costs that factor into some of these models. So how do you account for that when there's something that's truly novel and there's not extensive literature about performance, but we still want to make sure that we're factoring it in as an option?
Yeah, so that's a great question. I think one of the things that we want to be able to do is make underlying assumptions or sort of high level assumptions about a range of potential costs. And we can do this in many different ways, right? We can ask, okay, what's the average cost of a set of components by weight? And that's actually something that's widely used in the PV industry. You just, you weigh the cost of components or of electronic components, and you assign a cost based on weight. That's kind of a crazy concept for the water space, but I think that there are a lot of translational components that are used in other industries, and that we can extract a general range of unoptimistic or pessimistic cost estimates all the way up to what is the most optimistic cost that's maybe based either on the cost of raw material or, in the case of performance, is based on a theoretical limit. So a good example is in membrane distillation. For the ideal MD case, we assumed a membrane that had basically a permeability of just air. So there was no sort of barrier to vapor transport. And that was the upper limit of our statistical sampling.
Mm-hmm. So a follow-up question about some of the other alternatives that are out there. Quantitative comparison between the pressure-based membrane tech you talked about, and then emerging approaches like solar photothermal evaporation or freeze desalination, and in particular thinking about the challenge of actually coming up with a way of identifying costs. Like in solar, the energy is free, but there's lots of other costs that we have a hard time quantifying. So how do you think about evaluating those kinds of?
Yeah, that's a great question. I think one of the basis of these approaches all depend on process-based designs and optimization of those designs. So it's certainly constrained by having a straw man process. When we don't even have a straw man process, we can turn to things like understanding the thermodynamic energy efficiency of separation. And so there's still real value in understanding the thermodynamics. I also think, though, that the academic community has been over-dependent on thermodynamic analysis and has done a little bit less work in really thinking through how to implement some of these processes in actual operation and in ways that would affect costs. So I guess to succinctly answer your question, I'd say that for the lowest stage research, TRL research, you're certainly going to be focusing on primarily on operating costs, right? Because you don't have good system designs. But as you start to move into TRL 2 through 4 research, you are actually doing research on how you realize those kind of concepts in actual unit processes. And so these tools, I think, are best suited for looking at processes that are in that range of TRL level 2 through 4. Mm-hmm. And that's where NAUI is also focusing on their investments.
Great, that's really helpful. What are some of the opportunities for materials research? When we talked a lot about the RO designs, and we have Jin Hong and his collaborators and Seth from Argonne here and the materials manufacturing lab. So what are some of the frontier opportunities around materials in this space?
Yeah, great question. So I think in terms of high pressure reverse osmosis, there's a tremendous materials opportunity to really look at how to design membranes that are robust to higher pressures. There's a lot of material science that underlies sort of failure modes in these RO systems. So especially there's this thin film polyamide layer that sits on top of a polysulfone support layer. And what we tend to see in these high pressure systems is that your polyamide layer will kind of collapse into that support layer. And that can be really detrimental for water flux. We also see a compaction of the support layer itself, which essentially is reducing permeability of that support, which can also in fact impact your A and B parameters of the polyamide layer. So there's a lot of work in the material science realm to really get at how we realize better mechanical strength in these systems, how we avoid deformations that limit A and B in practice, and how we can also realize those improvements at sort of reasonable costs. The other thing I'll add here is that at high pressures, you're operating at high pressures because you're operating at high salinities. And so the thing that a lot of people don't understand about high pressure RO is that the permeate water quality that you get out is actually far lower than you might get from a traditional reverse osmosis system, because your B parameter might not change all that much. But because you have a higher feed, you're also getting a higher salinity feed, you're also getting a higher salinity permeate. So if you could also improve your B parameter, there's actually a lot of value there for high pressure RO systems. And that's really a polymer science question.
Got it. Yeah, I think that leads right into the next couple questions that I'm going to combine about reliability as a component in this model. So, you know, MD has reliability issues with pore wetting, high pressure RO has its other life cycle concerns. But when you're thinking about how to factor in the ongoing OpEx for reliability and serviceability and comparing among these, how can you do that with the model? Have you thought about that?
I mean, I'll just also add that MVC has horrible reliability problems when it comes to scaling. So all of these systems are suffering tremendously from reliability issues. And so what we are doing in these models is explicitly accounting for the need for membrane replacement on a sort of a defined basis. I think in both OARO and MD, we're assuming membrane replacement, or a fifth of the membranes are replaced every year. You know, that's a parameter assumption in our model. It's one that we can definitely tune and say, hey, we have worse reliability than that, or we have better reliability than that. But I also think that this question gets at the heart of membrane systems in general, which is that you can design very, very robust treatment trains by pre-treating the heck out of these systems. The issue is that pre-treatment also costs money. And so what these specific models don't do is address those relationships between pre-treatment and treatment costs, or treatment, I should say, between pre-treatment costs and reliability. Although within the NAUI community, we are working to build out those capabilities over the next year.
Great. So I'm going to combine a couple of questions about getting to the end users here. So when you're thinking about translating this information and getting it into the hands of people who are going to be making, their purchasing decisions based on it, what are some of the considerations that you've run up against in sort of translating this to the real world?
Well, I'll admit that this is pretty new research, and so we are, we're just starting to engage our industrial users to actually test these models and think about how this can help inform their preferences around technology adoption. But let me provide kind of a very specific example. And I don't want to call out the specific company, but there's an oil and gas company that has been really interested in MD for some time. And they've built a couple of systems, they've tested a couple of systems, they've done some cost analysis, but it's been very hard for them to ascertain whether this technology has traction, whether or not what salinity waters they should be applying it to, what the waste heat availability needs to be in order to make them cost competitive relative to an MVC system, how the lifespan affects the decision to adopt MD versus MVC. And so these types of models can really serve industrial user needs by clarifying, at least at a first order, what the kind of sweet spot for a specific technology is relative to other technologies. And again, where specific R&D investments might further reduce the cost of those technologies. So we're looking forward to working more closely with that company and other companies to rationalize their investments and reduce the risks of switching technology platforms.
Yeah. And I think one of the things that's really appealing about this methodology is the extent to which you can quantify the risks and sort of show how to selectively minimize them at different points through the process. And that's really valuable. I think, the final question I have is just how we get end users to work towards adoption of these novel technologies, because as you've acknowledged, I mean, even the industry, but also utilities, there's a sort of risk aversion that is part of the model of water and sort of working in water. So as you work towards, moving this even more into practice, how do you think about making the case?
Yeah. So I think that being very explicit about uncertainty helps to actually de-risk some of these investments. I think the other honest truth of this is that there are big transition costs. And so it's one of the reasons that we need large federal R&D investments in helping to facilitate technology development and technology translation over the next several years to decade. And I think we're seeing that, right? Like the Department of Energy has really stepped in as a leader in the R&D space for water, both through a number of the centers that are out of Argonne and Northwestern and other places, as well as through the hub. And we are also seeing some work out of AMO at an even higher TRL range, kind of the TRL 4 to 6 to 8 range, where the piloting efforts and demonstration efforts help to further de-risk these new technologies for the industrial end user.
Great. Well, it certainly will make, I hope, our federal R&D investors more confident knowing that you've got this great model to help identify where we can best spend those scarce and hopefully growing investment dollars. So I'm going to wrap it there, and thank you so much for this presentation. We really look forward to following the work. It was, again, such a great fit for the Third Coast community. So thanks for being with us. I'm going to share my screen just briefly one more time, just to let everybody know about our next, our next Third Coast, which will be the first of 2021 in our new year. And that's coming up on January 27th at 3 o'clock Central. And we'll have Dr. David Sedlak from UC Berkeley on 3 paths to solve 6 water problems. So stay tuned for more information about that. And thanks as always to my co-organizers who make this possible every single month and get such great speakers coming back time and time again. So appreciate it. Have a very happy end of the year to everyone and look forward to seeing you on the next Third Coast Water Seminar very soon. Take care, everyone.